Hi, welcome to the online lecture on vectors. I would like to start with the checkpoint question. Is there a place on Earth where you can walk due south, then due east, and finally due north, and end up at the spot where you started? Well, it turns out the North Pole would do that for you. Since going south and east would bring you to a certain position, but then in the end, going north, you would be right back where you started from. This is a clicker question, so I'll just let you think about this and then answer. You can just answer on paper, then we'll talk about it. For 1 hour, you travel east in your car, covering 100 kilometers. Then you travel south 100 kilometers in 2 hours. You would tell your friends that your average speed was, and your choices are 47 kilometers per hour, 67 kilometers per hour, 75 kilometers per hour, 141 kilometers per hour, or 200 kilometers per hour. So you should pause the video and try to figure out the answer to this. Then start playing it again. I'm having trouble advancing. There we go. So the answer is 67 kilometers per hour. Remember, the definition of average speed is total distance divided by the time. So your total distance would be 100 kilometers plus 100 kilometers, 200, divided by 1 hour plus 2 hours, or divided by 3 hours. 200 divided by 3 is 67. Your average velocity, however, that's a different matter. So check out the picture here. You've got 100 to the east, then you have 100 south. So what's your average velocity in this situation? Once again, pause the video, and then you can come back and answer. It turns out it's 47 kilometers per hour. Because this time you need the displacement, which would be the diagonal of this, the square determined by these two vectors. So you're going to have to use geometry and trigonometry in most cases when you're dealing with vectors. I would say the exception would be if they're just in one dimension. I spoke about vector representation in the pre-lecture. I also spoke about the mathematical reference system, but I want to remind you about it. We're going to use this, and your calculator is set up to use this reference system. So positive x is 0, and we measure angles clockwise if they're going to be positive angles, counterclockwise, I'm sorry, if they're positive angles. Clockwise gives you a negative angle. So 90 is positive y, 180 is negative x, and 270 is negative y. Now, two vectors are equal if they're the same length, the same magnitude, and they're in the same direction. So these two pink vectors here, a and a prime, are equal. They're equal magnitude, they point in the same direction. Vector b is the negative a. It's the same length, but it points in the opposite direction. So to make a vector a negative, you add 180 degrees to the direction. You reverse its direction, but you keep the length the same. Now, there are 3 ways at least to look at geometric vector addition. One of the methods is the head to tail method. So you draw the first vector, then you draw the second vector with its tail at the head of the first vector. And it doesn't matter which order you draw them in. The result is C. That's the vector sum of A plus B. The parallelogram method is the one that we will use most of the time because I find that it's easier to figure out which angles to measure for students if they use the parallelogram method. But they're equivalent methods. No matter what method you use, you're getting this pink vector C as the vector sum. So one thing you want to be building a neural pathway for is that when you're adding vectors, that's a specific process that's being called into action. It isn't just like normal scalar addition. So when vectors are in the same direction, then it is like normal addition. You either add them or you subtract them if they're in opposite directions. I think that should make a great deal of sense. If A is 3 to the east, 3 meters to the east, and B is 3 meters to the east, then the result is 6 meters to the east. If, on the other hand, A is 8 meters to the east and B is 3 meters to the west, then you have to subtract the 3 from the 8 and you get 5 meters to the east as your result. Okay, this was a checkpoint. Is it possible for the magnitude of the vector difference to exceed the magnitude of the vector sum? And slightly over half of you said no, it's not possible. But actually it is possible. So let's try to look at that. A is to the east, or to the west here, and B is at an angle of maybe 30 degrees south of west. That would be one way to describe that. Or you might say 180, and then this looks like about a 30-degree angle to me. 180 plus 30, that'd be 210, would be the angle of B here. So if you're going to find A minus B, what you do is you reverse the direction of B. So B now, instead of being 210, would be 30 degrees. You add 180 to 210 and then subtract 360. That's one way to think of it. Or you can subtract 180 from 210. So A minus B, I'm just drawing them head to tail here. The vector sum is, now we're just adding them, is this little yellow vector here. And yeah, that's probably all I want to say about that. It can be bigger, the difference can be bigger than A plus B. In this case, it isn't necessarily bigger, but it can be. Alright, let's talk about components, because that's what we're going to use most of the time to find our vector sums and differences. If you have a vector A, you can think of it as being two separate vectors, the result of two separate vectors. So here I'm showing A in the x direction and A in the y direction. And using trigonometry, the length of the x component here, A sub x, that's called the x component, is A, the length of the vector, times the cosine of this angle. And A sub y is A times the sine of theta. So what you want to do is write these down somewhere and realize that if the angle is in standard position, which is what we call it when the angle is measured counterclockwise from the positive x direction, then the y component is a times the sine of theta, and the x component is a times the cosine of theta. You're going to use that over and over all semester. So the signs, the SIGNs of the components depend on what quadrant the vector is in. In the second quadrant, the x component is always going to be negative and the y component positive. And in the third quadrant, both x and y components are negative. In the fourth quadrant, x is positive, y is negative, and of course in the first quadrant, they're both positive. If you always express your angles in standard position, the calculator will keep track of the signs for you. So let's look at the components of these vectors. If you have 60 meters at 120 degrees, one moment, I want to do